Hello, everyone. Welcome to another episode of the Blind Spot podcast with myself, Evan Thompson, and Marcelo Gleiser and Adam Frank. And today we thought we would talk about the planet, as in Earth. And this is where we end our book, The Blind Spot. We have a chapter at the very end on Earth system science, and that includes discussions of things like the Gaia theory, which arose due to the work of the atmospheric chemist James Lovelock and the microbiologist Lynn Margulis. And this was an idea that I think was put forward in their work first in the 1970s and then developed through the 80s and 90s. And the basic idea is that the Earth, the planet, is a self-regulating system. That is, the planet, including the oceans and the atmosphere and the rocks and the biota, the sum total of all life, makes up a self-regulating system. And when this was first proposed, there was a lot of enthusiasm and interest in the idea, but there was also a lot of criticism. And as a result of the criticism, James Lovelock decided to devise a model that is a basic feedback cybernetic model to show how the temperature could be regulated by the planet as a whole system. And he called this the Daisy World model. And it involved the growth of different light-reflecting species of daisies, dark and light daisies. And Adam has recently, with some colleagues, done a, update of the model, a new version of the model. So we thought we would begin with Adam describing maybe the original model and then how the new model takes further steps and what kind of questions it raises about the Gaia theory and how that would then be developed through further modeling and testing.
Yeah, so the Gaia hypothesis and Lovelock and Margulis, if I could just step back a little bit and tell a little bit of this story, because in my book, The Light of the Stars, I did a deep dive into it, which was a lot of fun. And actually, the idea goes all the way back to Vladimir Vernadsky, the greatest scientist you've never heard of. Vernadsky was a Russian biogeophysicist. He actually invented biogeophysics and was really a bold thinker. And it was in a series of lectures in 1927 or 4 in Paris that he introduced the term biosphere. He is the one who came up with the idea of the biosphere. The idea being that, that the sum total of life was a geological force. Before that, people kind of saw the plants and animals as being just kind of like some kind of green scum floating on top of the ground or the water, and it didn't matter. And he was the one who said, no, it has completely hijacked and changed the planet. He also, by the way, which we might want to come back to, introduced the idea of the noosphere, which was that, human, which we now call the technosphere. The idea that humanity and its machinery, so to speak, technology, was also now adding another layer on top of the biosphere. So fast forward to the 1960s, James Lovelock is an independent scientist, kind of an atmospheric chemist who'd made enough money with this device he had devised for testing small amounts of chemistry that he could do whatever he wanted. He was pretty much independent. And NASA, young NASA, 1960s, early 60s, hires him to do experiments about, hires him to, they were thinking about sending probes to Mars to test for life. And he's sitting here listening to these guys talk about looking for microbes on Mars. And he's like, you're just looking for Earth life. How do you know there's going to be Earth life on Mars? And it's in thinking about this that he realizes that atmospheres are life detectors. And we use this, right, as Marcelo knows very well, in astrobiology now, that it's the chemistry of the atmosphere is completely changed if there's life there. For example, we have oxygen in our atmosphere. It's only there because of life. So it's out of this that Lovelock begins to think about atmospheric disequilibrium, atmospheres being pushed into places that they wouldn't normally be by life, that he develops the Gaia hypothesis, that life is sort of this driving force which changes the planet, but changes it in a way just like homeostasis, basically. If you drop me off in Antarctica, my internal temperature is going to be 98.6 degrees. If you drop me off in the Sahara, my internal temperature is going to be 98.6 degrees. So Lovelock introduces this idea and then brings on Lynn Margulis also. So there's a story we'll get to later about Carl Sagan's role in all this, which is amazing. And Lynn Margulis actually provides him with the mechanism for this to happen, which is microbial life, that it's really the feedbacks mainly from microbial life that will actually, if the conditions on the planet get too far away from what life needs, then feedbacks from the microbes will happen that'll change conditions to bring the planet back to those conditions. So this kind of idea that how do you respond to a perturbation? All right, so anyway, that's a little bit of background. The important thing is that biologists hated Gaia. And they hated Gaia for a bunch of reasons.
Some biologists, not all.
That's true, right? Some biologists, but people like Richard Dawkins, etc. But one reason was cultural, right? The New Age loved the Gaia hypothesis, in part because the name, right? It was named after the Earth gods.
And it was William Golding, the novelist, who, in conversation with James Lovelock, suggested that it be called the Gaia hypothesis. Eventually, the Gaia theory.
Right. And then I think because Lovelock wanted to call it Earth System Regulatory Theory.
Something like that, yeah.
No hippies were going to... I have a photo. It is hilarious. I showed it every talk. And it's a picture of Oberon and Mary Beth, or not even Mary, Oberon and Morning Glory. And they are priests of Gaia. And they this is a picture from the 70s. They're wearing their tie-dye robes. And the best part is, between them with their tie-dye robes, is a baby unicorn. Yeah. I mean, I swear to God, it's a goat that they put a horn, that they glued a horn on its head. And so, so there were like Gaia rituals, Gaia festivals, Gaia choirs, and so the scientists sort of, I think this was the background. People had their own objections to the idea, hardcore objections, but also this cultural sort of countercultural embrace of Gaia didn't help. So finally, bringing this story home is Lovelock and, oh my God, Watson. In response, this is before I think even Lynn Margulis was brought on. They wanted to show that this idea that a biological system could exert feedbacks that could control perturbations, because that's all it's about. It's about like, oh, the Earth's getting too hot, and then the biosphere has to do something to bring the temperature back down. They wrote this very simple mathematical model called Daisy World, where you had the planet, you had the star that the planet is orbiting. The star is slowly heating up, which is exactly what stars do, right? Stars slowly increase their temperature. And if there was no life on the planet would slowly heat up in response as it absorbed the solar radiation. And so what they showed was if you had two species of daisies, a white reflective daisy that would bounce the sunlight off into space, and a black absorbing daisies that would absorb radiation, then what could happen is that, and depending on how they respond, what their growth curves were like what temperature they liked, you could get the black daisies to start growing when the planet was cold and raise the temperature, right? And keep it at one level. And then as the star got hotter and hotter and hotter, eventually the black daisies would die and the white daisies would start to grow, and they would reflect the light, keeping the temperature constant. So you would get billions of years of the temperature being exactly constant, perfect for life on the planet, while the temperature of the star continued to rise. And this was an example of a feedback. The daisies were providing a feedback that kept the planetary temperature exactly where it needed to be. So that's the Daisy World. And that, in many ways, sort of quelled the criticism. They showed criticism was still there, but they showed a simple model that, this could work.
So the black ones absorb the heat, get hot, and so the atmosphere gets a little colder for that reason. And then the white ones reflect the heat and warm up the atmosphere. Is that how it goes?
No, I think it was more about that. You had to assume, we're getting into the details there, you had to assume thermal convection was pretty quick. So the daisies, you have to assume there's some amount of ground that is not, and I hope I'm getting this right. If I'm getting this wrong, excuse me, I have to go back and look at it again. But yeah, there's one of the assumptions is that, the not thermal convection, but conduction, that basically the planet equilibrates, the ground equilibrates to the temperature of the daisies very quickly.
Okay. Yeah. So there's no atmospheric coupling at this point.
No. Or if there is atmospheric coupling, it's very fast and it but I think it's really about the ground that really matters. Okay. In fact, I'm not even sure there is an atmosphere in this. There's an albedo, right? What really matters here is the reflectivity of the planet and the absorptive properties of that's where you get the albedo.
And my memory is that it's the albedo, it's the change in temperature as a function of the changing albedo with the differential growth of the black and white daisies. That's my memory
Right.
of it.
Yeah. The more white daisies you have, the more the more you're not absorbing the solar radiation,
Right.
the more black daisies you have that. Yeah.
Yeah.
Right. So the albedo is essentially a fancy word to explain the reflectivity of a planet.
Yeah.
Right.
Yeah. How much? It's about how much of the incoming sunlight you actually get to keep to warm you up. That's really what it is.
Right.
Exactly.
So it's, I mean, I think the analogy is sort of, the glaciers, the ice on the planet versus the forest canopy, light and dark, but stripped down to these two species of daisies. That was the rationale behind it, as I recall.
Yeah. And that's exactly, I mean, so if you look at the real Earth, there is this complicated feedback for albedo is incredibly important. Right now, the Earth's albedo, I think, is like about 30%. So 30% of the sunlight hitting the Earth bounces back into space.
Yeah.
If you were to absorb more of that radiation, if it was 25%, not 30%, then 5% more solar radiation would be absorbed and the planet would be very different, right? And so, ice controls how much ice you have on the planet, controls your albedo. How non-ice ocean
oceans, right?
Also. The oceans are dark. The ice is reflective. The forest canopy has a different reflectivity. So this is an example of real world Earth systems coupling. The Daisy world was this pared back version of what is really happening on Earth. And as climate change happens, where people are worried about the changes in the albedo that will occur from all these links.
Right.
We should probably also know when we talk about Earth system science, what are the systems? There is atmosphere, right? The veil of gases around the planet. There is the hydrosphere, which is all the water, lakes, rivers, oceans. There's the cryosphere. You have to treat the frozen water differently as a system than the liquid water. There's what's called the lithosphere, which is just the ground, right? Not all the way down. You're not interested, though it couples, you do have to think about it, the deep mantle that's 1,000 feet down, but it's really the crust, the upper layers. And then the biosphere. So before we go on to what we did, is there anything else we should say about? So this is sort of the history,
Well, maybe one thing to point out is that the criticisms that were the early criticisms that were made of the Gaia hypothesis by people like Dawkins and W. Ford Doolittle, and those criticisms were basically, well, you're supposing that the Earth is a biological individual, but the only way you can get biological individuals is from evolution by natural selection, and there's no population of planets that are competing reproductively, and so there's no selection mechanism, and so this is just a silly idea. And what's interesting about that criticism is that it makes a fundamental kind of conceptual mistake, actually, which is that the proposal is that you have emergent macroscopic dynamic phenomena that are arising out of lower level, lower scale in space and time interactions, and that's a perfectly scientifically intelligible and tractable kind of thing to propose. It's just being proposed in this very novel way for the planet as a whole. So the issue isn't that the Earth came about in some reproductive competition with other planets through selection. That's not the proposal at all. The proposal is that there's a kind of emergent biological or biogeological individuality. You have all these interacting component systems, and then the Daisy world model was an attempt to give a stripped down bare illustration of that idea using ideas from cybernetics that had to do with feedback and self-correcting systems. So there's this intersection of what today we would call Earth system science, but that word didn't exist then, intersection of ideas about the planet with ideas coming from systems theory and cybernetics. And that was really Lovelock's kind of like genius moment. Well, he had many genius moments, but that was certainly one of them, where they, this intersection of abstract system theoretic ideas from cybernetics with these much more, concrete ideas that integrate geology and biology and atmospheric chemistry and so on.
Can we talk a little bit more about cybernetics, about the history of cybernetics? Because I'm just becoming aware of this, myself in sort of reading. I've been reading this giant 4-volume set put out by the Santa Fe Institute, Santa Fe Institute, called Foundational Papers in Complexity Science. And it goes back to 1920. And it's like paper after paper that set what we now call complexity science, which all three of us are very interested in, how these ideas are emerged. And there are from the 40s, a couple of papers by Norbert Wiener. Is that?
Mm-hmm. Yep, Norbert
So
Wiener.
can we talk a little bit about, you seem to know more about cybernetic, theory than I do. I don't know, Marcel, if you want to chime in too, but I don't really know. I know bare bones what cybernetics.
Cybernetics is the origins of what today we think of as complexity science, also the origins of what today we think of as cognitive science. And it was a field that's, depending on how you want to date it, emerges. There's work that goes back to the 20s, but it really starts to come into formation in the 40s and 50s. Through work by figures like Norbert Wiener, who I think proposed the term cybernetics. Cybernetics comes from the Greek, and it means the steering person or mechanism in a ship. So the idea is that cybernetics is the science of entities or systems that are able to adaptively regulate their behavior in a way that looks purposeful, in a way that looks like agency is involved.
Agency.
Exactly.
I want everyone to know we love that word. We're going to be coming back to agency quite a bit.
Yeah.
And it it drew from mathematics and biology and anthropology, basically anybody interested in thinking about systems in their structure, organization, and behavior. And it's the roots of what today we think of as deep learning, neural networks, and artificial intelligence, because that goes back to the fundamental contributions of Warren McCulloch and Walter Pitts, the logical calculus of ideas immanent in nervous activity, this absolutely foundational paper, 1940s, I think.
That's in the
volume, right?
Series, the volume as well.
Exactly. So this was work being done at MIT that basically looks at the nervous system as a self-correct computational system. So that's core to cybernetics. The idea of autopoiesis, that life is about self-production at the cellular level, that comes out of cybernetic work in a sort of second generation of work by Umberto Maturana and Francisco Varela. And there's a very important convergence of that stream of work with the Gaia theory that we can also talk about. But I'll hold off on that. I'll come to that later.
No, I think that's beautiful. I mean, I read Wiener's book a long, long time ago, and I always thought it was about, can we make sentient machines eventually, by coupling machinery to information theory and stuff like that, and feedbacks, and how do you make a robot move in the world? So it has to sense the world, it has to adapt to what it's seeing, so there's this idea of I didn't know the word came from what makes gives direction to the ship. That's perfect, actually. So it makes sense, right? I mean, if you think of a planet that self-regulates that way, it is, I'm sure the roots are right there in cybernetics. To me, it's perfect.
Yeah, and I guess there was like second order cybernetics at some point. People started thinking about, well, what happens when the steerer knows itself as the steerer, right? Is that right?
So second order cybernetics, so this is really linked to work by people like Heinz von Forster and Gregory Bateson, where the idea is that in cybernetics, you start out with, this is very related to ideas in our book, The Blind Spot. In cybernetics, you start out with basically the idea of a system. But what counts as a system depends on the observer, and the observer is itself a system. And so second order cybernetics sort of explicitly brings the role of the system into play and the need to understand the observer. And that generates a whole new, I suppose you could say, discourse. And it's in that context that the idea of autopoiesis arises. And actually, so maybe I will say something about autopoiesis and Gaia at this point, and then you should tell us about your updating of the Daisy model, Daisy World model. And this has to do with my father, actually. So my father, William Irwin Thompson, he ran an organization called the Lindisfarne Association. And in 1980, I believe it was, he organized a conference that was held at the Green Gulch farm, which belongs to the San Francisco Zen Center. So this is in Marin County. So this was a Lindisfarne Association meeting, and he brought together James Lovelock and Lynn Margulis, whom he already knew, and Francisco Varela and Umberto Maturana, the architects of the theory of autopoiesis, whom he also already knew. and a French information theorist, theoretical biologist named Henri Atlan, and also Heinz von Forster, one of the leading theorists of second generation cybernetics. And the idea was the rationale for this meeting was to bring the Gaia theory thinkers together with the second order cybernetics and autopoiesis stream of research. And it was at that meeting that basically Lynn Margulis and Francisco Varela and Roberto Maturana sat down and talked for hours, where Maturana and Varela explained the theory of autopoiesis to Margulis. Margulis explained, and Lovelock explained the Gaia theory to Maturana and Varela. And out of that came the idea that what Gaia is either an autopoietic system or something analogous to an autopoietic system at a planetary level. So it provided a whole new kind of conceptual vocabulary for thinking about life at this planetary self-production level. And that then particularly influenced Lynn Margulis's writing about the Gaia theory going forward.
Were you at this meeting?
I sadly was not. I was in my first year at Amherst College as a freshman, and I missed, but I was with them, all of them together, some years later in 1988 in Perugia, not far from where Marcello is, Perugia in Umbria. There was a second version of this meeting that also brought together all of these people. And Lovelock presented Daisy World model, and Varela's response to the model was that this was an important step forward, but it was important to go deeper and to use ideas about biological autonomy that he had been working on with others to go beyond the just feedback conception of emergent individuality, that Daisy World was still working with basic sort of kind of, you might say, simple feedback mechanisms, but there was a whole new rich world of what today we call complexity theory that actually was really the tools that needed to be used to talk about Gaia as a individual system.
I always love your stories about like when you were 18 and all these incredible, these foundational thinkers. When I was 18, I was smoking weed and listening to Meatloaf,
Well, this meeting in Perugia,
you were also, hanging out with
this meeting in Perugia, I was a grad student. I was a grad student at this point at this meeting in Perugia, and I was working with Varela. And I was utterly terrified, but I gave a talk to the meeting, and this was like one of the first talks I ever gave.
Oh my God!
These people are in the audience, and on the one hand, they're friends, and they're very friendly and loving and supportive, but on the other hand, I'm absolutely terrified. Hey, come on.
Well, that's always an important thing I think for people to understand about science is that we are in general, we're friends, we like each other, but we'll rip each other a new one when it comes to ideas. I mean, politely and gently, but in general, and that's good, right? In general, when it comes to our ideas, we're going to be, we're going to slice and dice. So I think it's true. Even though you're in front of friends, they might still spread the idea that they love you, but they might not love your idea.
That's a way of showing love if it's done right.
If it's done right.
That's really true. That is
exactly
really
right.
Yeah. Well, just related to, so this is unrelated to our topic, but I'm going to tell the story anyway, because it's a great story. So when I was about 14 years old, I was, living in New York City at Lindisfarne in Manhattan. And Francisco Varela was a scholar in residence. He was living with us. And a philosopher came to give a lecture, and the philosopher talked about Plato and Plato's theory of the forms. And I was studying, classical Greek as part of my education, and I was reading philosophy. And Francisco Varela asked me after the talk, "What did you think of the talk?" And I said, "Well, I actually don't really think that this description of Plato's theory of the forms was really right. It's not like Plato thinks there's a chair and then the form of the chair. The forms are these more abstract mathematical principles." So that was just me talking to Francisco. And then we were sitting after the lecture, all having, I don't know, a drink or coffee together or something with the person who had given the lecture. And the person who had given the lecture asked me when they found out I was studying Greek and I was in philosophy, "Oh, what do you think of my lecture?" And I said, "Oh, I really liked your lecture. It was very nice." So after this was over, Francisco, no, I didn't say anything.
You didn't do that,
I just said,
however.
"Oh, yeah." And then Francisco came up to me afterwards and he said, "You shouldn't do that. You should never do that. You thought the lecture was wasn't good. And, the person asked you, you have a responsibility to say you thought it wasn't good, and don't ever do that again." And he was doing it in this older brother avuncular way.
Yeah.
It really stuck with me. It was like, oh, I was just trying to sort of be polite. I was a little scared. I didn't want to, like criticize the person. And then Francisco said, no, you have to say what you think, and you have to tell them, no, I think you're wrong. That's what you have to do. So that really stuck with me. Anyway,
that's a great story. Yeah, because a lot of what I have to deal with in some of my public writing is when it comes to like conspiracy theories. I just had that New York Times op-ed a couple of weeks ago about the manosphere and what it does to science, and trying to get people to understand that, like, scientists and scholars, there is an ethics that goes along with it. Like, none of us are making a whole lot of money from what we've done. We do it, not for, it's a comfortable living, but we do it because we believe in it. This is our identities are caught up with the principles of scholarship and honesty and transparency. And there's an ethics that comes with this that we really live by, because what else do we have?
So update of Daisy World.
Okay. So Daisy World. So what did we do with Daisy World, and why did we do it? So just some background, which is the question, as you were pointing out, that Margellus and Lovelock, and the question really is not whether the Earth is a living, individual. It's whether it displays agency, right? Whether the Earth is an agent. And this is something that the three of us right now are very interested in. We're doing the three of us in the podcast, we've been talking together about it quite a bit. The idea of a physics of agency, which would of course be more than just physics. It would be biology and information theory, and computational theory. But what makes an agent? An agent is a system that has self-awareness, right? Is present in its environment, but it also is creating its own environment, right? When we talk about agency, we talk about autonomous agencies. An agent has its own purposes and decides for itself about what it's going to do, right? So the question really here is Gaia an agent, right? Because if we sort of follow the history, if we just go back to the history, Gaia theory remains pretty contentious in the scientific community. But what happens is as climate science is rising, this new field of thinking about the Earth takes huge amounts of ideas from Gaia theory, or from Gaia theory, and it kind of they sort of like put the name away because they don't. It's like, oh, this is too contentious, and it starts to be called Earth system science. And there could not be a science of the Earth's climate, or really anybody else's climate on any other planet, without Earth system science. And for the stuff Marcelo and I are doing, when it comes to biosignatures, searching for life in the universe, this idea of planetary systems, water, ice, etc., is fundamental. So the Gaia theory sort of transmutes into Earth system science. But the main idea of Gaia is still a kind of unproven, which is that the planet the biosphere exerts control, right? That the biosphere is truly homeostatic. It can actually reverse perturbations to keep itself healthy. Because if it did that, it would be agential. That's what we would talk about being an agent. When a cell, a chemotactic cell, so that we've probably heard of us use that word before. Chemotaxis is when a cell moves up a gradient of nutrients in order to get more nutrients, right? It's following the candy trail, right? So that's an example of agency. The cell is like, oh, food, I like food, more food, I'm going that way. Can the biosphere, can a planet with a biosphere be agential? And to do that, our idea, the three of us that we've been talking about, and there's others who are part of our collaboration, have the feeling that this really involves information. That really the idea here is that what makes living systems, i.e. agential, and I think we'd all argue that every living thing, from a cell on up, is agential, is the use of information. Unlike other systems. Yeah, go ahead, Marcel.
I was just going to throw a question, actually. Do we associate automatically? Probably the answer is no, but still, agency with self-awareness. I think that's what messes things up with Gaia, because people say, come on, are you saying that the planet actually has some sort of purpose or intentionality? And I think that's what pisses off a lot of the scientists, which are more conservative in the way they look at things, right? Yeah, I don't know if anybody has an answer. No, I'm just saying, I don't think anyone has an answer to that. It's just like, I think that is one of the complications of this question.
Right. And that's what we're Go ahead. Sorry, Evan, go ahead.
No, I would just say, I think it's important to separate questions about awareness when we use that word in a way that suggests consciousness or sentience, it's important to separate awareness, let alone self-awareness, from questions about a system being an emergent individual that operates autonomously, where that means that it's made up of interacting subsystems or sub-processes that are all entangled in a way so that it functions as having a unity or a kind of wholeness that involves adaptively regulating itself so as to maintain that unity or wholeness. It's important to separate that question from questions about consciousness or sentience or awareness. Even if at the end of the day they come back together, you can't sort of a priori assume that they're going to be together from the start.
Right. There's no conductor in this orchestra in a sense.
Right. Right. The Earth, there's no, right, exactly. The Earth, this view does not require that the Earth has, sort of, right, a consciousness that's like, oh, I love life and, and I love
unicorn.
What? Unicorn. My unicorn.
Right.
Yeah. And so, what Evan was describing, there was a bunch of things the words there, about organizational wholeness, causal closure, these are really powerful ideas that need to be explored and have just the hints of being explored beforehand, right? I mean, in the sense of especially from a physics perspective, there are these leading thinkers who in the 70s, 80s, and 90s began to sort of push in that direction. But I think there's what's really exciting from our perspective is there's so much work to be done to try and understand what agency means from a, informational, physical, thermodynamic, biological point of view that hasn't been done before. And you can separate, as you said, you can separate that out from is there a consciousness in there? Because that's you don't need to jump right to that question for this perspective to be mind-blowingly profound to me. That a system that is physical can have this property of agency, because one of the things that will come out of this, and I'm sure we can devote a whole episode to this, is the idea of co-emergence. That one of the things I think that we're very interested in is that when a system becomes an agent, the environment also becomes the environment, right? What is the world like by itself, without us? I have no idea. You know what I mean? It's kind of Kant's thing in itself. I don't know if there's anything you can say. And this was the whole point of our book, of The Blind Spot. What can you say about the world independent of us, right? Nobody ever gets the world independent of us. And so one of the things that sort of comes from this perspective of agency is that, of course, there's a world without us. It's just not this one, the one we're living in. And that may be true for every agent. That the environment becomes a meaningful environment full of things you want to pay attention to only when the agent becomes the agent. So no self, no world, no self in that sense. World meaning environment.
Right. So it's an open question whether the planet, with the proper name Gaia, is an agent in that sense. And that could turn out to have been a very, fruitful idea for generating research, but it might turn out that that's not actually how it works, even though the interacting systems of the planet interact in these, dense, complex, nonlinear ways that involve some kind of mutual regulation. So that, I assume, is what's behind the updating of the Daisy World model, right? So maybe describe exactly what you found, or how the model works and what you found.
Right. So the question, we believe, that one of the directions that the three of us with our collaborators are pursuing is the idea that agency has something to do with information, right? And that all agents store, copy, transmit, process information. Unlike rocks. Rocks don't do any of those things. You can describe a rock in terms of information, it's the location of the atoms in the grid, but the rock doesn't care. You could also use other methods to describe rocks. Whereas with agency, with life, you have to think about information. So what we wanted to do, because we are interested in this question of whether or not the Gaia or the biosphere is agential. And I kind of think it is. That's my bias, but I could be wrong. We took the Daisy World model and we converted it into we had to find a way to be able to cast it in information theoretic terms so that we could do an analysis of it in terms of what we call semantic information, right? So this now leads us in a whole other direction, which I won't take us down very deeply, but just there's a difference between the kind of information the kind of what you think of as information that your computer is based on, which is called syntactic information, which is just basically, it's all about probabilities about whether a particular symbol in the alphabet is going to show up. Oh, E is used a lot, so that has this probability, and X doesn't get used very often, so that has a different probability. There's no meaning in that. What we're really interested in is how information, which is kind of inherent in the word, in the colloquial sense of the word, there's a knower. There's something to be known, and there's a knower. So we had to cast the Daisy World model in a way that we could do a information theoretic analysis of it and look for semantic information. So we've been studying semantic information for a while. And by the way, this was all done by our postdoc, Damian Sawinski. So he was really, Damian is so smart. He's the one who figured out how to do this. And basically what was really interesting is, because one of the fundamental things with information theory is it really matters, fluctuations really matter, right? This is, you really have to think about like, this is statistical. There's the temperature's going up, the temperature's going down, temperature's going up, temperature's going down. You need randomness in order for any of this to make sense. So what he did is he figured out how to put it, we focused on a planet that was orbiting a brown dwarf, right? Not something Earth-like, but something that's, that is orbiting very close to its star. Because for not brown dwarfs, excuse me, M dwarfs, these are stars that are half the size of the Earth. Yeah, and they have much, their habitable zone, where a planet would be warm enough to have life on it, is very close to the star. These things have 1 week orbits, right? It takes us 365 days to go around the sun because we're pretty far from the sun. These things are parked right up against their stars. And they have flares. They have very powerful, solar storms. And so that's a fluctuation. Like the planet is constantly getting whammed on by these flares. And so that means the temperatures are always experiencing fluctuations, even though overall the star is heating up, like the star is slowly heating up. Now there's a lot of noise in it. So anyway, that's the background. So we were able to do a information theoretic analysis of the daisies and how the daisies were making their switch. And what we found is the important point was a semantic information threshold. And this is something we've seen in our other models of semantic information, how semantic information works, meaning how systems that use meaning acquire meaning. And this is, like, again, lots of detail. We won't need to go into it. But what we've always found in these systems that are using semantic information, that are gaining meaning, is that if you look at their information gain as a function of sort of like what their interactions are with the environment, those systems will show like very flat, if you add a bit of information, nothing changes. If you add a bit of syntactic information, nothing changes. And then you get to a point where suddenly, wham, it goes like the amount of semantic information rises very steeply. It's as if suddenly, like, I'm very metaphorically here, wakes up, right? And we found that the Daisy world has that kind of change, that once there's enough sort of linking between the daisies and the planet, you get a point where the daisies suddenly go through a semantic information threshold. So it was just, it was the beginning. It was, there's a million miles to go. But we showed that you can think about Daisy World in a semantic information way, where you can think about the daisies getting meaning, responding to, being, having a causal sort of internal state representation of what was going on. So it was a first step in sort of thinking like, maybe, in Daisy World, you can see a sense perhaps of agency in these black and white daisies.
This would probably open up a bigger discussion, and maybe we'll do it in some future episode, but I'm curious if you can give just a little mini description of what semantic information in your model is. So if we think of, say, syntactic information as given in terms of bits, which are just purely quantitative, formal syntactic things, what is semantic information in your model?
Yeah, so this comes from a paper by Kolchinsky and Wolpert in 2018. And I actually found that paper because when I was writing the paper on planetary intelligence, which at some point we may want to talk about as well, because I knew that, if we want to think about a biosphere as having some kind of, intelligence, and by intelligence, I just meant cognition, that it's aware of its own state in some very abstract sense, semantic information. And there was no paper, there was no mathematical theory of semantic information up until then, or at least not a very good one. And in 2018, Artemy Kolchinsky and David Wolpert wrote a really beautiful paper that was kind of as Artemy would say, it was a manifesto for a mathematical theory of semantic information. And the idea is very simple. Imagine you've got a squirrel and it's in a forest, and the squirrel has hidden its nuts all around the forest, right? And now you come along and you move all the nuts, right? So the squirrel has lots of information about the forest, right? The squirrel's in the forest, and there's sunlight in the trees, and there's that bush over there, and that. But there's not all of that information matters for the squirrel's survival. So the way the whole formalism of semantic information works is you start off with a situation, and you've got lots of information, which are correlations between the squirrel, what's going on in the squirrel's head, and the environment. And now you scramble all that information, right? And then you kind of rerun, so you do a simulation of a squirrel living in a forest with this situation. And so how long does the squirrel live, right? Well, it knows where its nuts is, so its nuts are, so it lives a long time. Now go back, scramble the information, move the nuts, rerun the simulation. How long does the squirrel live? If you moved all the nuts, it's not going to make it through the winter, it dies, right? So now what you can do is you can bit by bit, you can move, one piece of it, remove one piece of information at a time and rerun the simulation. And what you'll find is you'll be able to figure out, of all the information that the squirrel has in its head about the forest, about the environment, of all the correlations between the squirrel and the environment, you can figure out which ones are meaningful. The meaningful ones are the ones that contribute to its viability, to staying alive. And so this formalism that Kolchinsky and Wolpert did, it was like, it's highly mathematical. They had one little model. And so our job, we had a wonderful grant from the John Templeton Foundation to do this, and we were partnered with Artemy, is to try and operationalize this. We started applying it to a bunch of different situations, and we found that actually Artemy's and David's intuition was exactly correct. This threshold, this whole idea of a threshold, is exactly what occurred in system after system. So it's really this idea of there's lots of information, there's lots of syntactic information, but it may be that most of it just doesn't matter to you. It has no meaning for whatever your goals are. Your goals, right? You have goals. Nobody gave you those goals. You have those goals as a agent. So that's how it works.
So it's almost like a phase transition from not a lot of information is needed or relevant to just the right amount that gives this viability curve, its jump. And then too much information is also useless. So that two genes, right?
Right, exactly. Yeah. So once you reach the plateau, then the extra information now doesn't matter. You don't need it, right? It's really, and so this, like you said, a phase. So in physics, there's this powerful idea of a phase transition, that a system will be like disordered. Like think about a bunch of magnets, little magnets in a row, and they'll be whatever,
They're pointing all
Marcelo, explain the phase transition.
Yeah. So, well, the one with magnets, right? So you have like a bunch of little magnets, and they can point in this direction or that direction, like even polar ones that we use, like north-south ones, right? Just disorganized in a box kind of thing. And then you apply an external magnetic field, and then they go, whoop. They all go in line with that. So you go from a disordered state to an ordered state. And
it depends on temperature, right? I mean, if the temperature matters, if it's very hot, it won't, they're all bouncing around and they won't align with the magnetic field. But as you bring the temperature down, they all lock in. Yeah.
Yeah. There's a competition between the strength of the outside magnetism to align things, and the noisiness that comes from the agitation from the temperature. And so there is a critical temperature where alignment below which, as you decrease the temperature, all these magnets going, okay, let's align now, because there is not a lot of heat making everything agitated. And so that's a typical example of a phase transition. There are a bunch of others, like water going to ice and water. But that's the idea. And so whenever you have either is a continuous but fast, abrupt change, or even a discontinuous change in a system, we talk about the phase transition, and then we say first order, second order, continuous, discontinuous, And this one looks to us, that was our paper, right? The PRX one looked to us like a continuous, it wasn't like a bubble nuclear. It wasn't like that. There was an amount of information where there is a critical amount that is relevant for the thing to be alive.
Right. So I think, we're almost there. We're at 47 minutes, so we should probably close out. But let's close out with that question, right? So what was so exciting about this is like the possibility that agency, right, which is, getting back to our question, agency, to me, agency and sentience are kind of linked. I think all agents have a degree of sentience, not necessarily self-consciousness. I'm like, oh, I'm a cell, I want to go find more sugar, but just like this sort of basic internalness, awareness, presence. But is that an informational phase transition? I think that is so exciting.
It's almost like, I was just having this idea. It's like a metabolical urge that gears the organism into action. So it's not necessarily, a mind or anything like that. There's a metabolical urge, which we of course call hunger, but it wouldn't be hunger. It would just be an imbalance in the system that forces it to realign its goals, in a different direction. And there may not be any deep kind of conscious or whatever you're going to call this mechanism there, but it's a seed that will eventually become a more sophisticated thing that could give rise to a self-awareness. But maybe in the beginning, for very simple models and organisms, it's just like there is an imbalance in the system that forces it to behave in certain ways.
But it still requires that phase transition, right? So that's why like a thermostat is not what we're talking about. It's still this idea of you have to create these levels of organization, of architecture, the architecture of the relationship in the networks and the network itself in order for this phase transition, so that you go from a rock, rocks, nothing's happened to a rock, to suddenly this thing which is agential. So it's like, it is discontinuous or whatever. It's not, in the sense that like something has to happen, something remarkable has to happen.
Well, maybe there is also a selective aspect to this, in the sense that the organisms, want to call these agents, whatever, that do not have an efficient enough mechanism to transform metabolic depression into action will not survive. And the ones that survive are the ones that have enough reach into this information from the environment that will, propagate, will propel them into action so that they can survive. So there may be a combination. So the complexity of how this metabolic depression works to propel motion or action, right? The motility of the thing may have a selective pressure there. The optimized ones are the ones that have the ability to go over the hump. I don't know, I'm just daydreaming here, but
this is great. I mean, for our audience, this is what.
Yeah, sounds like we need another conversation to talk about agency and sentience, and work on that question. But we can't do that one today.
Yeah, but I think that was for people listening. This is how projects start, right? So Marcelo is, presenting an idea. I would be, probably want to push back a little bit, but then it's out of this. This is like what our conversations are, over beers or whatever, where it's like, wait a minute. And then like suddenly it evolves and it's like, well, how do we test that? Or how do we formulate that? So that was that's a beautiful little, like, this is how the game gets played, and the joy of it, right? The creative.
I was going to say so much fun, because
it could be much fun.
Most of the ideas are, but when it's right, it's really awesome.
Oh my God. Yeah.
All right. I think we should stop there, everyone. Thank you very much.
Thank you. Yep. So we'll see you next time.
In a couple of weeks, hopefully.
Yep.
Bye.
Bye. Bye.